past 8. It's now past 8:30, so we'll get started. We have a slightly lower turnout than usual. We had some glitches in the mailing and reminder system. So anyways, I wanted to thank you all for being here this morning. I know that for some of you it took a lot because you had other things going on, and to take time to come today to this webinar, whatever you had to do to organize that to happen is really appreciated here. And my commitment to you is that you get some value, take home value out of this webinar that you'll find useful. Okay, so with that, we'll get started. The topic today is simplify workflow, reduce FTEs, and increase output. And this is the 6th of a series of webinars which we have had on process intensification. So before we launch into that, I'll just give you, for some of you who are not familiar with us, who it is that we are. So who's in this room? Well, I'm the founder and CEO of the company. I've been with the company for a long time, and we've developed a whole generation of products focused on what we today call process intensification, but everything to do with improving productivity in biomanufacturing, particularly downstream processing. And we have a 30-year history. We have novel products. 30 FDA-approved drugs are using our products in manufacturing. So these are not technologies that are not proven. They're proven, they're used, and to benefit by many companies. We have over 200 global installations. And in the last few years, we are particularly proud of the fact that 2 major COVID vaccines have been made using our equipment. And we are talking about hundreds of millions of doses, right? And so there's over $20 billion worth of biological drugs and vaccines being used or being made using our products. And we are inventors of radial flow chromatography, which is a term most of you may be familiar with. Some of you who are not can certainly reach out, and we can discuss those with you, though that's not the specific topic for today. And QuantaCept chromatography systems and skids. So we have a whole line of instruments from the bench to large scale for chromatography, multi-use, and then also single use, so with disposable flow pads and sensors and such. And then our latest offerings are in the area of continuous chromatography, whether it's a 2-column or a 3-column system, whether it's a bench scale system or large scale system, and a buffer dilution and buffer blending systems. These are very distinct. Buffer dilution is not the same as buffer blending or stock buffer blending. We'll discuss that. And all these make up what we call integrated and intensified bioprocessing. So, which means that we are combining multi-unit operations. So no longer do you have to make buffers for chromatography, but these can be done in line as part of the chromatography system. All right, so why are we talking about process intensification? Well, cost is a big driver. Workflow is a big driver. FTEs in the realm of shortage of talent, utilizing what we have to our best advantage is very important. Of course, having more production out of the same plant, if you've got $150, $200 million plant, getting even 1 or 2 batches or 3 batches or more product out of that plant just adds to the profitability, because your capitalization is the same, the workflow is the same, and you're able to produce more output. So for any process engineer like myself, we've grown up with that we have to make processes more efficient, right? So on the left, you have a traditional workflow for a traditional biological manufacturing plant, where you've got your seed train, your reactors, separators, chromatography systems, chromatography columns, TFF, concentration, final fill, and finish. And, on the right, you can see the number of days associated with each of these steps. And so the entire batch could take easily 6 to 8 weeks. Some cases more, some cases a little less. Okay, so if you're doing fed batch, maybe a little less. If you're starting fresh every time, obviously more. If you're doing perfusion, you can cut it down considerably. So that kind of gives you, and so these slow batch processes are synonymous with long cycle times, right? So the longer, and since you have multiple steps that are transfer and hold points, right? Where you go from cell culture to filtration to centrifugation to chrome capture to viral inactivation. So you're taking samples at various points, and you have whole tanks where the product after each of these steps is being held. So until you get QC results, you can't often move to the next stage. And so it's very cumbersome, takes a lot of time, takes a lot of effort, and takes a lot of FTEs, right? And eventually all this filters down to cost of goods, right? So how many batches are you doing? How much is your output from the plant? How many people? What's the capital? What's the materials? And of course, there are plenty of examples that you'll find from different companies who've given presentation over the years of how long their batches take and how long it takes to optimize. And this is particularly true for CMOs, right? Where they're going from one product to another. And each time, for the innovator company that's making the same product, things have been optimized. They can go a lot faster. But for CMOs, it's particularly an issue because they have to start from, square one each time. And so here's kind of an anatomy or cost structure for a typical plant. We try to simplify it, 8-week cycle time, plant output, let's say 50 weeks, so 8 batches a year. If you've got some overlap between batches, you can get maybe 10 batches a year. A large capital investment, always take a moderate plant of $150 million and you amortize the capital over 10 years, so it's $15 million a year, about 70 people in this plant at, a labor rate. Usually we've taken a lower labor rate, burden labor rate, maybe as much as $450 an hour. And that's about $25 million a year. Materials and utilities, about 10 million a year. So, and the output from a typical plant like this may be 100 kgs, so cost of goods is $500 a gram. So in the best of cases, that's about where we are, right? And of course, if these drugs are going to be more affordable, more accessible, and this is just the cost. So there's lots of obviously regulatory, other overhead on top, which is significant. So then at the point of treatment, these costs become fairly high. And, in our world over here in the Western world, it becomes easier. It's because of our insurance system and all that. But, in the rest of the world and what we are calling the global South these days, it doesn't translate. And a lot of these treatments are out of the realm of affordability. And of course, we as bioprocess engineers can affect that positively. So as we go through and design these plants, what constraints, and we purchase equipment, what constraints do our choices from facility to process equipment and choices of the equipment, choices of the facility, choices of the process strategy have on the plant output, on our FTE requirements and workflow, right? So that's the conundrum of bioprocessing. And bioprocessing intensification is a buzzword that's being used, but under its umbrella comes these kinds of answers, or at least tackling these choices as opposed to just doing a cut and paste. See, if somebody's has to scale up, they merely cut and paste, and buy bigger columns or buy bigger equipment, along the lines that they've always been doing. Well, the result is that you're going to have what you had before. And we know that biomanufacturing uh, people by nature are conservative because we have to operate in a regulatory framework, and making any changes, you know, lends lend themselves to scrutiny, to validation, to questions by regulatory authorities, by internal QA teams as well, which slows the process down, takes a lot of effort. So change is a big deal, and change management is a big deal in biotech, but it has fruits as well. So here, for instance, we've talked about this in other webinars when we talked about facilities, but we had discussed this small little blueprint for a conventional plant where you had at the bottom, you have a corridor here, the upstream corridor, and you've got the upstream inoculum, upstream suites. And as you round the corner on the top are the downstream suites, right? So you have the seed train, media prep, and cell culture here. Round the corner, you have the DSP suites, but you have buffer making, buffer prep, column packing, etc. And you have these corridors, which for supply of materials and personnel into these specific areas of the plant. There are lots of other footprints, but we are just dealing with one for sake of simplicity, right? And as the titers go up in cell culture, which is very often the case, well, the DSP suites get stressed. They have to move to larger and larger chrome skids, larger and larger columns. And of course, the buffer prep areas and the column packing areas get stressed because you don't have enough buffer to support larger installations. You might be able to fit in larger skids and columns, but being able to increase buffer capacity by 4 times, 5 times, 10 times, that's not so easy. And then these areas the space becomes rate limiting, the people become rate limiting, and of course, storage of these buffers, right? Where are these buffers stored? So very often they're stored in these corridors. Of course, there are new plant models out there, which I'll share with you, where that's been taken into account and streamlined so that you have buffer storage and you have more totes and such that you can use. Right? But this is the conventional response, which is that you have bigger columns, more chrome skids, more cycles, more head count. So you're adding head count, you're adding cycles, adding more documentation, QC, etc. And the indirect consequence of this is that you're making more buffers, you're requiring bigger square footage of the plant, more gray space support, infrastructure support. So very often walls have to be knocked down, time frames are shifted back, and in order to accommodate these changes, right? So change doesn't come free of cost necessarily. So the topic today really deals with, what are the choices that we can make around equipment? What are the choices that we can make around process strategy to really get ahead of the curve and not have these kinds of issues come and dog us when in fact we are looking at scaling up, right? So one is, of course, the choice of a column, right? Conventional columns, work great on a lab scale. You can do a little modeling on, um, little 3 millimeter columns, right? The problem is, of course, that when these are scaled up to a meter column or 2 meter column, um, the flow rates, you can whiz through these columns, you can have very short cycle times, don't necessarily work. And we look to guidance from vendors or manufacturers who may say, oh no, but in manufacturing, you should have 20 centimeter bed height columns, even though you might be doing something in a little high trap column and it works fine. Well, because we've got to pack these columns, they don't quite work as well if you have short bed heights. So all of a sudden, there are major changes being made that were not factored into the original design. And the pressure issues, large space requirements. Conventional chrome systems also tend to be kludgy. and you're just basically running flow through the columns. And so then the big question becomes buffer management. You have larger stainless steel tanks. If you're, of course, you don't have those tanks in the areas where you're running your column, so you have to meter the flow to chrome skids that are in the storage in the purification suites, or potentially outside where you have to fill up totes, and so I'm moving these totes in and out. And then, of course, there are hold steps between batches. So where do you store that material? So anyways, those are all the choices that come before you that you need to confront. And so, this is not our work. This is just work that you guys can do. But this is just work from literature where they show, like on the left top, you'll see this, I'm sorry, a well-known CMO, right, which has 2 facilities. They have 4 cell culture suites, 2 purification suites. They have 3 media and buffer areas, prep rooms, right? So they have to make 5,000 media buffers. I do 106 column packs a year. So, you just look at, and they have 3 production schedulers in these 2 plants. So lots of complexity around that. But basically, take home here is that you have 30% of the operations dedicated to buffer prep, right? And of course, lots of batches being done, so lots of scheduling activity. So the batches are not separate. You can dovetail them, right? You can overlap them. On the right, you see again, buffer prep area, about 1/3 of the area of the entire plant. And, our Bioforum did a survey, and people have gotten more efficient with automation and such. So I take this, I think we can do a lot better than this, but 2,000 liter buffer took 7 hours and 2 FTEs to make, right? So going through, right from getting the raw material, mixing it in tanks, QCing it, transferring these to bags or to totes, again, ensuring that the pH, conductivity, etc., is right, and sterility bioburden is okay, and things are properly marked. So all that, takes a fair amount of time. Now with automation, you can certainly reduce a lot of that, right? But the point being that we are spending a lot of time, not directly on process, but non-process things. Column packing is another area which can be time consuming, especially if you're doing a lot of packs. So people are looking at pre-packed columns as a result of that. All right, cleaning and validation of the plant can become a big deal. So single use has come about. All right. So now we go to process intensification. Process intensification is all about reduced cycle time, reduced footprint, increased output, and reduced cost. So in previous webinars, we've taken each of these topics and delved into them, right? So the last webinar was about reduced cycle time by 4x. The previous webinar before that was about reducing plant size and reducing footprint. The next one we'll talk about reduced cost. They all dovetail into each other, but it's good to unpack these things and deal and go into each in more detail. So here we are going to talk about increased output. And bioprocess, for some of you who may be thinking about bioprocess intensification as something new, yeah, it's coming. Yeah, we ought to look at it someday. Well, that was the case in 2015, 2016. You had about 50% of the people starting to look into it. And today it's become really a transition, a transformation is happening where 2/3 of the people are informally evaluating it, and you have 1/3 of the people are actively in the process of implementing and evaluating. So what is process intensification? One is the need for continuous processing, right? So we have been in pharma industry, we have been a batch culture. Everything has been batch oriented. You make things in batches, you qualify the batch, you validate the batch. You've got, batch uh, numbers for, your batch release criteria. So everything's been batch. The FDA has told us now that they want us to transition. It's a guidance from the FDA, not us, but the FDA, okay, who have given us guidance to move to continuous processing. And certainly we see more of an impetus in the industry doing that with high density perfusion cultures, right? That's already starting to happen. And less so in downstream, but we have certainly developed tools for continuous separations, continuous chromatography, whether it's continuous centrifugation, continuous chromatography, continuous ultrafiltration. And people are starting to work on implementing these, plugging these into different unit operations. But that itself isn't going to carry the day, right? Because if you implement a continuous operation in one place in a process train, and then downstream, upstream, you've got batch processes, well, guess what? It's like a weak link, right? So the slowest part of the process is going to slow down the entire train. So process integration and connectedness are very, very important, right? So we need to integrate all the parts of the process so that even the slowest part can be speeded up, can be integrated, and doesn't become a bottleneck. So integrating buffer generation with continuous chromatography, if you're going to run continuously, it's wonderful, right? But if you're going to make buffers in batches, doesn't do anything because then the process has to stop. Or you've got a bucket brigade of buffers that need to be changed out constantly from these continuous process. So, and then continuous, a lot of times people are talking about just continuous capture. But, if you take an antibody model, there's a continuous flow through step. There's continuous TFF, there's viral inactivation. So we have to really look at interconnectedness of these different steps, whether it's continuous capture and continuous flow through chromatography, for instance. Right. And then, of course, with these, if you want to minimize hold steps, then what can you do in the way of online or outline monitoring to look at parameters, right? That will then help you get the data so you can move that process along and you don't have to hold material. So anyways, we find today that we are moving from fed batch to continuous upstream, which is what is shown on the top. And I think the idea now is really what the industry, few pioneers in the industry, I would say, are looking at is continuous process all the way end to end. Okay, there are very few factories that have actually done that, and I'm here to advocate for that. And this is what I was telling you that in 2013, Janet Woodcock went to the Congressional Committee about modernizing biomanufacturing and bringing about continuous manufacturing platforms. And in 2017, CEDAR finalized the guidance for the move to continue for bringing about innovation and modernization in biomanufacturing. So that all relates to continuous manufacturing. So you have the FDA behind you. You don't have the FDA, you don't have to convince the FDA. The guidance is from the FDA. And of course, you have to, as with any change and change management, you can't do it willy-nilly. And you have to ensure that you're still going through change management in the appropriate way and validating the changes that you're making, whether it's batch or whether it's continuous. So what are the benefits of continuous processing? Well, certainly small footprint facilities, less FTEs and more output right there, right? So on the right-hand side, you can see a model of a batch plant with the same output, right? So it's significantly bigger, significantly more complex, larger tanks, So column sizes can be reduced by as much as 10x. Okay, buffers don't have to be batched in large tanks because the process is always going on continuously. So you can have, ongoing buffer need requirements, which can be continuously generated in smaller quantities and smaller flow rates, as opposed to waiting like 4, 5, 6 days, 7 days when a huge batch comes, and then you have to make all these buffers and process those things right away. And until that batch comes to that particular unit operation, it's not being used. That equipment, that part of the facility is not being used. Then suddenly the batch comes there, it's used, then it goes to the next uh, unit operations, and then first unit operations not being used at all. So, the efficiency of usage in batch operations of the entire plant, when you look at it from that perspective, is very poor. Whereas in continuous processing, the cell culture is happening at the same time as the separation, as the chromatography capture, as the flow through, as the viral and active post viral inactivation, post-viral inactivation processes like UF. So all of these are maybe a little bit staggered if you still have to have some hold points, but for the most part, it's continuous, right? At least that's the vision, that's the drive. That's what I'm talking about here, right? And whole tanks have to be QC'd in the batch plants, so you don't have any of that. All this requires more footprint, extra tanks, more QC people, more buffer handling vessels, etc. And in this day and age of global warming, we cannot dismiss the amount of waste, whether it's the number of totes that are required for batch operations that have to be disposed of, even if you're doing single use. But in continuous operation, that's not the case, because you're continuously running that process. In each batch, you're not taking out all the tubing and bags and all that, tossing it, which is a big sustainability issue, right? It is certainly in the US and also in Europe, and will be more so globally. So I think we are being good global stewards as well in terms of sustainability and moving to this kind of process strategy of continuous production. And, in batch processes, like I said, everything is staggered, integrated processes. Even in continuous, they're happening together. There might be a small amount of staggering, but you can see the whole time is significantly shorter, right? And there are different strategies you can use where you can have multiple unit operations. Depending on the titers, you can have multi-column processes, you can have two-column processes, you can have three-column processes when you go from, after, we are assuming that you're running a perfusion bioreactor and going to continuous clarification. So after that, you can go to simulated moving bed where you have maybe 4 columns or 3 columns, or you have continuous steps of the Pro-A step or an AEX step and a CEX step or AEX and HIC or Pro-A mixed and AEX. So these can be somewhat staggered, moving to nanofiltration for the last one. We are removing salt. Okay, so how can Seprogen simplify your process, right? So we've kind of given you a sense of what the issues are with current processes and what it is you can do with continuous process to reduce FTEs and increase plant output. And what can Seprogen do in this regard? Well, there are lots of novel things. To some of these are old, but for some might be novel. One is, of course, columns. You don't want column flow rates to become an impediment or a bottleneck. So radial flow columns can be used. These have been proven. For people who are interested, you can contact us, we can discuss. But you can typically reduce the cycle time by 4x. Okay, but the main thing we are talking about here is continuous chromatography, where again, you can reduce the cycle time significantly, where you're continuously, you may have 2 or 3 columns, which is, so one is being loaded while the other is going through the wash elution regen cycle, and then flip back and forth in a continuous manner. So you have continuous product coming out all the time, and your harvest is continuously directed to the columns. right? And sometimes you may have 3 columns where the output from one column goes on to the flow through from one column goes on to the second column to maximize the capture of the first column. And then while the third column is going through the regeneration process. Now, what we've done in addition to that, which is very interesting, very unique, and certainly makes continuous chromatography more enabling, is that we've integrated buffer blending into the Chrome systems, right? So you don't have a buffer blending unit or a buffer dilution unit where you have to take the output from that and put it in the buffer tanks and then run your Chrome skid, continuous chromatography skid. No, no, no. The stock buffer solutions, whereas the acid-base components of the buffer and the salt, concentrated salt and Wi-Fi, are all integrated into this continuous processing skid. And you run your continuous chromatography, simply put in the molarity, the pH, and the conductivity of the equal wash elution buffers. And each of those concentrated buffer components are mixed with water behind the scenes. And that particular buffer is created on demand and delivered to the column. So this enables, so there's no buffer prep needed at all. Buffer prep is gone. And so no additional FTEs are needed. And so you can run your operation continuously while the buffers are being generated. And then you can shrink the plant down further if you can take, this continuous capture and integrate it with continuous flow-through chromatography, again with integrated buffer blending and with nanofiltration all on one skid. So you're getting this essentially closer to a plant in a box type concept where you're integrating these things and the buffers are right there being made on demand so you can be far, far more efficient. We've done several projects like this, and you're welcome to talk to us about your requirements. So I'll quickly go through, what we have in the way of our continuous Chrome systems with integrated inline stock buffer blending. And we are calling these systems QuantaSep Fusion. So Fusion Elite and Adept Elite. The Elite means that we have integrated stock buffer blending, and the Adept means that you can still have continuous, but you can have the continuous systems in single use flow formats. So you can remove the entire tubing and or you can install one with all the sensors which come sterilized and remove them. So you can have single use and continuous and integrated with buffer blending. In this particular, we don't do that with the bench scale systems, but this is a bench scale system. The orange just shows on this little PNID or graphic chart, which is there on your computer screen running the process, just shows the harvest going from one column to the second, while the blue is the buffer, which is going through the first column, which has been saturated and does the wash solution, regen, etc. And you've got all the standard sensors of pH, conductivity, UV, etc. And we've got automated recipes. So lots of different recipes can be run using these machines, and you can look at the chromatogram trends, change valves, all that stuff. Right, and this is meant for manufacturing, so the software is 21 CFR Part 11 compliant. And then what is the difference? People often get confused between inline buffer dilution and buffer stock blending, right? The inline buffer dilution simply means that you may make a 10x or 15x concentrate of the equilibration or wash or elution buffers. Sometimes you can't do that with elution buffers because if you're eluting with 1 molar salt, you're not going to have 10 molar salt concentrate that you can dilute tenfold. And then these concentrates are diluted by Wi-Fi in the Chrome system to give the final 1x buffer. Sometimes you can do the dilution, it works fine, but the pH may not be, pH may be off. So you have to deal how to handle it. Some of these systems can't run gradients. We can run gradients, no problem. But what we are talking about with stock buffer blending is that we have actual concentrate of the acid and base component of the buffer and the salt. So now if you have a monobasic phosphate solution, 1 molar and 1 molar dibasic phosphate and 3 molar salt, you can simply dial in, like, I want 0.05 millimolar phosphate at this pH. And the system will just blend those in the right flow rate in line and give you that buffer on demand with the right conductivity and pH. And that's really while you're running your continuous process. So you're not going to make that buffer, put it in a tank, and then take it to your continuous process system. No, no. This is all, these concentrates are just hooked up online, these stock solutions that you can get directly from a factory. Just hook it up online, in line on the skid itself, and make all these buffers. And if the buffer is out of spec, it goes out of the system for a minute or so until it hits steady state, and then that's delivered to the column. So very simple. And we have continuous skids. Down here, for instance, we have, this is a 2-column skid running in a pilot plant. And down here, you see these different outlets. So that's Wi-Fi, acid component of the buffer, base component, and then salt. And you have different outlets. So you can have actually multiple buffer systems. So you can have acetate, an acetate buffer system with sodium acetate and acetic acid or phosphate or tris, right? So it's not just one buffer you can make multiples of these buffers. The second skid here is a flow-through skid, where you're actually going after viral inactivation through an AEX column. Then the salt is adjusted and the pH is adjusted in line. So prior to going into the AEX column in a flow-through mode, then the salt is adjusted in line, and then it goes through a HIC column, and then goes through a nanofilter, or it may go through a CEX column, while all the buffers are being, for elution, are being also can be made on that particular skid. So lots of integration of these systems enabling continuous flow through. So basically with these two skids right there, you can connect them to a perfusion bioreactor, let's say with a cell separation device, and go straight into your capture flow through, and then pre-TFF, right? So very, very powerful, very compact plant. And this is kind of the HMI, picture of the HMI that you're going to be running. So that's your harvest line going through either column 1 or 2. And on the left here, you see pump W, A for acid, B for base, and C for the salt. I mean, well, not C for the salt, but the pump C is salt. So these are run in different proportions to give the right buffer with the right molarity, conductivity, and pH, which can be, sent to the column that's been saturated while the first one or the second one is loading, right? And you can take samples pre-column, you can remove any of the air, any off-spec buffer can be removed, and your product is collected here. We can also do viral inactivation and make sure that the pH in the elution tank is at the right pH and held for the right amount of time before it can transition on to the next skid. And the next skid is this, where again you have your buffer blending, and then this is the raw material at the bottom coming right in, adjusted with the pH. So it goes through the AEX column, then again adjusted with the salt, go through the HIC column, going through the nanofilter now, right? So again, flow through mode, so everything goes one pass through the column. Potentially can be connected to a single pass TFF as well. And we've got different recipes, automated recipes that you can write for both of these columns. We've got event log, alarms, inline calibration, controlled access. We can connect to somebody's DCS system through OPC UA. can upload data. We can connect to a network. We have login authentication connecting through a network. So we have a whole software team here, PLC team, that can work with your particular engineers who are designing the process and implementing the project. And again, more of the same, where we're basically telling you how we've integrated the flow-through steps. And then here's a picture of our bench scale single-use continuous system. So here, the flow path is completely removable. So we have two flow paths, 0 to 100 mils a minute, 0 to 300 mils a minute. And it's a 3-column system. So we can either integrate the buffer blending part or not. It's your choice. So in the smaller systems, the buffer requirements are not very large, so there's no need to do that. But in larger systems like this, which is being used to make a therapeutic antibody, a biosimilar antibody, where you have a 3-column system, you've got inline buffer blending, the whole flow path is removable and comes pre-sterilized with all the sensors. That, of course, is a larger scale connected to a 2,000 liter perfusion. So now you really need to do inline buffer blending. So the software and all that for that has been developed. We used the same philosophy a few years ago when we were called upon to do one of the largest skids in the world, 125 liters a minute chrome system. And making buffers at that scale would have been really problematic because you're going 7,500 liters an hour. And so it was incumbent that, and they didn't have in that plant the capacity to make the buffers nor the square footage. So we created this machine with 5 different pumps so that the buffers could be made in line along with Wi-Fi and harvest. And regardless of what the buffer was, whether it was 200 millisiemens or 175 or 150, you can see the parameters, the tuning was done such that in very short order, right, the particular set point was met. It was always delivered to the column at the right pH and the right conductivity. So that's the other thing. If your input is slightly off, right, which may happen with buffer making, the output, the system's smart enough to ensure that the output is always the same. So that was on a very large scale. Here's some data from actually a 3-column capture system. So this is, again, the orange is the load, first column being loaded, and the flow through from the first column going on to the second column. So that way, even if you hit breakthrough on the first column, well, the breakthrough curve is always like sigmoidal, right? So, typically people stop at the bottom of the breakthrough curve. But, in a situation like this with expensive resin like protein A, you can keep overloading the first column till it hits the top point of the breakthrough curve, right? And the column is truly saturated. And whatever didn't bind then binds to the second column, right? Well, while the first column is going through the wash, elution, and regen. And then once this column is saturated, then the blue line, then the buffers would move to this column. And then the third column would become the leader column, and the first column would become the follower column for the load step. And when you do elute from this buffer blending system, you can see that, we may have 1 molar phosphate, monobasic or dibasic, and then 3 molar salt, but we are making 10 millimolar solution for equilibration, right? There's more than a 22x turn down. You can see how fast that happens, how stable it is. And then there's the wash solution. The same thing on the pH. You can just go from 7.5 to 3.5 pH very, very quickly, right? Not easy to do, but we can go both ways very fast. And then lastly, I'd said that for some of you who are interested, we'll just touch on radial flow, though that's not the main topic. And we had said conventional columns are slow. In radial flow columns, the flow goes to the entire outside wall of the column and travels. And so there are two concentric frits where the resin is held between these two frits. So a very large surface area over which you're applying your flow. The flow is diverted to the entire outside wall of the column, goes through the outer frit, through the resin, through the inner frit, and out the bottom. So very short beds. The bed depth now is the radial distance between these two frits. And for binding and elution types of separations, which is ion exchange, affinity, and all that, it gives you superior performance, higher throughputs, and lower pressures, and it's eminently scalable. In fact, linearly scalable. So if you double the height of the column, you have twice the area, so you can run twice as fast. The bed height, which is the radial distance, remains the same. So the back pressure remains the same. And because the volume of resin has doubled, you can load twice as much. So everything is scaled up in the same proportion. And this is data just from a study that Genentech did and shared with us that with conventional axial columns, their runtime was 8 hours, whereas with the radial flow column, it was 2 hours. Okay, so the low-hanging fruit. We've got lots of these machines out there, lots of these columns out there. You simply slurry pack this column by priming the column from the bottom with buffer, driving the air out, and then pumping the slurry in through these ports until the column cavity, annular cavity is packed, the pressure rises, that's it. Stop the packing, empty the slurry lines, run in the forward reverse direction, and check the HTTP and asymmetric. So, large installations here for 350-liter radial flow columns in a particular process running over 20,000 liters of raw material every day. In the dairy industry, we have these columns where they are doing a million liters of milk every day. We have automated column packing skids. And as far as the performance is concerned, on the right, you see at the bottom, you see the impurity profile. And you can see that in terms of product recovery, monomer, HCP, DNA, and leach protein A, it's equivalent to any previous conventional column that they were using. So, and as far as the continuous process is concerned, you can see that you can streamline your facility very easily, right? So here here are the stock solutions that are prepared, the media, and then you have, upstream, downstream, post-viral, pure processing, because on your chrome skids, you basically have you basically have concentrated stock solutions. That's it. So you don't need big storage spaces for totes and studs and management of the buffers. You don't need any of that. And you have continuous processing going from one step to the next to the next. So your footprint is down, the FTEs are down, and of course the output is significantly higher. Right? So what is the output? Increasing plant output by 4x and reducing COGS. So now, even if you have some hold points, you're running continuously, right? So you're continuously producing product. But maybe the continuous process is still, TFF or till the concentration step, but not really bottling. So you still have a batch component to it. And so let's say the cycle time is 2 weeks. So now you're doing the effectively 24 weeks. 24 batches. And because your facility is much smaller, we've taken out the facility down by a third because you don't need all that buffer management. The chrome systems themselves are much smaller, columns are much smaller. So your amortization is 10 million a year. You can run this with about half the FTEs, so that's 12 million a year. Material and utilities will still be the same. But the output of the plant has gone up by 2.5 times, and the cost has gone down from $500 a gram to $130 a gram. So again, major reduction in cost, increase in plant output, and increase in efficiency. So this is the future. The future is coming to us, whether you embrace it or not. Other people will, other companies will, and your competitors will, right? So we are here to support you. And as you look at going from this process, which is at the bottom, which is kind of this kludgy process, batch process to continuous, you can see where, we can support you, whether it's in continuous capture, continuous flow through, columns, etc. And we are happy to hold your hand and work through whatever issues you might be having. And we can, we can have confidentiality agreements signed and discuss with you how we can support you in making your process more intensified. And so in conclusion, whether it's with continuous capture chromatography, continuous flow-through chromatography, continuous chromatography with inline buffer blending, or actually even if you're just wanting to do traditional chromatography but want to bring inline dilution or inline buffer blending as part of the chrome skid, we can do that. And we can provide you with single-use systems and, of course, radial flow columns, all of which go to intensifying your process. And that's our commitment to you. So, and as a company, we deliver what we promise. So I'm going to stop sharing now, take a few minutes to answer any questions you might have, or you can reach out separately to us and we can do a one-on-one. But again, I hope you got something of value from our webinar today. That was my commitment. And we are done 5 minutes before the half hour, and I'll take any questions you may have or put them in the chat. Well, I don't see any questions. Sanjit, do you see any questions in the chat? None, right?
I do not. No.
Okay. Well, then I'd like to thank you all very much again for taking the time to come to this webinar. I know for some of you it was, you might have had to give up on other things and take time away. So really, really appreciate it. And I hope you got the value we promised. Reach out to us if you have any questions. Think about it. If you want to brainstorm, we are here. Thank you very much and have a good day. Bye-bye.